Okay, hello and welcome to the Radical STEM Homework Help Livestream for March 9th. There we go. I was waiting for the video preview to catch up to me. Trying out a new streaming setup that will hopefully work better. So, yeah, if you have homework questions in math or science that you need help with, then you can put them in the chat and we will do our best to help you solve them live. So, in the meantime, until we get any viewer questions, I'm just going to be working on some math problems to pass the time. Let's start with some calculus. Okay, so this is going to be an improper integral because as this function is going across these bounds from 2 to 5, right there at 2 we're going to have 2 minus 2 in the denominator, which will give us a denominator of 0, and that's going to be a problem. So what we actually need to do is replace that lower limit with a new variable. Let's call it t. And then we will take the limit as t approaches 2. And I guess we would want to do that from the positive side of 2. So, now we can go ahead and evaluate this integral how we normally would, and then we'll deal with this limit after it's evaluated to see if this is going to converge or not. So, let's see what we can do here. X minus 2 squared. If we let u equal x minus 2, then that would mean that the derivative of u with respect to x is d dx of x minus 2. And when we take this derivative, we'll just distribute that d dx onto both terms. When it hits the minus 2, the derivative of a constant is 0, and the derivative of x will just be 1. So for here, we're just going to get 1, and then we'll multiply by dx to bring that to the other side. So du simply equals dx. Now, our integral will equal the limit as t approaches 2 from the positive of, we actually will have to rewrite our boundaries, but the inside of our integral will now be u squared on the bottom with du on top. Let's think about our boundaries here. We have x going from t to 5. So when x is 5, u would be 5 minus 2. So our upper bound will be 3. And similarly, when x is t, u would be t minus 2. And now this is just going to be a polynomial integral that we can use our power rule with. I'm just going to rewrite it as u to the negative 2 du. That makes it a little easier to see our power rule. So let's go ahead and do it. So this will be the limit as t goes to 2 from the positive of u to the, we'll raise the exponent by 1 and divide by our new exponent, evaluated from t minus 2 to 3. And put it down here. That will be the limit as t goes to 2 from the positive of, let's bring this negative out front. We'll have 1 over 3 minus 1 over t minus 2. And I can already tell this one is going to have some problems. It's not going to converge. If we just go ahead and do this limit, the 1/3 won't matter. We could basically just say this is minus 1/3 plus the limit of this term. And when we do that, when we take this limit as t goes to 2 from the positive side, we'll have like t being 2.5 minus 2. So it's going to be a positive number, but then it's going to get to 2.1 minus 2 and 2.000001 minus 2. And we're going to keep dividing by a number that is closer and closer to 0, which means that this fraction is actually going to become infinite in value. So this whole limit is going to diverge, and with the negative here and there, that should be diverging to positive infinity. So we're actually going to have the conclusion that our original integral I does not exist. And that happens sometimes with improper integrals. That was fun. Let's try another one. Okay. So, this one might look a little funky, but it's actually just going to be a polynomial integral by the end of it. We're just going to have to do a little algebra simplification to get it there. So, let's actually calculate what x minus 1 over x squared really is. Actually, I'm going to do that just in a separate line, and then we'll rewrite our whole integral. So x minus 1 over x times x minus 1 over x. If we distribute that, we're going to get an x squared. We'll get a negative x times 1 over x, or a negative 1. We'll get another negative 1, and we'll get a positive 1 over x squared. So it'll be a minus 2 there in the middle. Now we can say that our integral is equal to the integral of x squared minus 2 plus 1 over x squared dx. And let's go ahead and just break this up into smaller pieces. We'll use the linearity of the integral to say this is the integral of x squared dx minus the integral of 2 dx plus the integral of dx over x squared. And then we can just evaluate each one individually. So, first one, integral of x squared, we'll use our power rule. It's going to be x cubed, and then we'll divide by our new exponent. Over here, the integral of, well, the 2 comes outside of the integral, and the integral of dx is just x. Now for this one, let's rewrite that fraction. Say that's x to the minus 2 dx, just like we did before. And so we're going to get x to the negative 1 divided by negative 1. And since we just evaluated all these indefinite integrals, we're going to get a plus c, our constant of integration. And that's pretty much it. The only other thing we can do is just simplify this term. Can just bring that negative out here, and if we want, write it as a 1 over x. And that is our final answer. What to do next? Okay, I think we'll do the physics problem next. So we're going to have a square with point charges at all 4 corners. and we need to find the electric field at the center of the square when we have our charge Q being equal to 10 to the minus 8 coulombs and our side length A being 5 centimeters. E equals. Okay, so to start, we'll say that the electric field at the center that we're looking for is going to be the electric field from plus Q, the electric field from minus Q, the electric field from 2Q, and the electric field from minus 2Q. Because I should put a plus there as well. That's just the concept of superposition. So when you're here at the center, you're going to feel the electric field from this one, and that one, and that one, and that one, all at the same time. That's all that this is saying. So that's going to be our final answer. Now we just need to write all of these in a vector form and then add them all together. So let's start with plus Q. So E plus Q. Just to save myself some writing, I'm gonna use the shorthand for the formula. So the electric field from any point charge is KQ over R. Or, yeah, in general it's KQ over R. Here the charge is a positive Q. And R is going to be this distance. But we need to do a little geometry to get that. Luckily, once we do that geometry one time, all of these corners are going to be the same distance away from the center. So let's see. We have triangle. This whole side length is A, and each of these sides is R. Since this is a 90-degree angle, this would be 45, which means that also this is 45. And half of this is A over 2. That should give us enough to get it. So if we just look at this bottom 45-degree angle, I'm gonna erase that one. If we look at this, the adjacent side is A over 2, so we can relate the adjacent and the hypotenuse with cosine. So cosine of 45 degrees is equal to A over 2 divided by R. And then that means that R is equal to A divided by 2 times the cosine of 45. And if A is 0.05 meters divided by 2, And cosine of 45 is, oh, brain don't fail me now, that's square root of 2 over 2. It's been so long since I've done that, I feel like I need to double check myself, but I'm going to roll with it. Then this will just be some decimal number. While I calculate this, I'm going to double check my cosine of 45. Oh, also, since it's on the bottom, that would be 2 over the square root of 2. It would be the reciprocal. Cosine of 45. Okay, yes. I was not crazy. So that means this 2 and this 2 cancel out, and we end up getting 0.035 meters, or 3.5 centimeters for this R length. So I'll put that up here. R equals 3.5 centimeters. Okay, so now we can come up here and actually get a number. Also, I suppose since we have this vector hat here, we should address that. We'll say this is the magnitude. Okay, so our K is really a stand-in for 1 over 4 pi epsilon naught, and that, I believe, comes out to 9 to the power of 9 when we condense it into that K. We have our charge being 10 to the minus 8 coulombs, and we've got 3.5 times 10 to the minus 2, but squared. So let's simplify this. Get 9 and 3.5 squared. We'll have a 10 to the 9th up here, a 10 to the 8th down here. This becomes doubled, so that would be a 10 to the minus 4, and then we can bring it on top to make it positive, 10 to the 4th. That will give us 0.734 for these leading numbers, and then we would have times 10 to the 5th Newton. No, that's not right. This is an electric field, so it would be volts per meter. Let me double check that simplification just in case. looks to be about right. Yep. So that is the magnitude of our vector. And because it's pointing just diagonally down, it'll be an equal amount of this this will be equally distributed in the vertical and horizontal directions. So we can actually say this is 7.34 times 10 to the 4th. And if we make this a vector quantity again instead of just the magnitude, we could say it's times the vector minus 1, 1. No, that's not right. So we need it to be equal in both. We don't want a full 7.34 pointing in both the vertical and horizontal directions, but we want it to be equally shared between them. What is, let's see. Oh. We want the magnitude of that to be, you know what, we're just gonna roll with this being the magnitude for that for right now, and then we'll deal with all the components of these later, because I bet with these all being multiples of the same charge, we're gonna end up with some cancellations, maybe. If we reduce it all to numbers, we won't see those cancellations, because that's probably going to come from having plus and minus multiples of q. I know I just did all that calculation, but I think I'm going to actually try it a different way. Now that I just thought of that. So this electric field from plus q will be some x component and some y component. The x component will be the magnitude of this vector times cosine of 45. Since 45 is the only angle we're going to be working with, I'm just going to call it theta, so it's shorter to right, and that will be in the x hat direction. And similarly, we'll have that times sine of theta in the y hat direction. And because that's the same term in both of them, we can factor it out. So we'll have the magnitude of E from plus q times cosine theta in the x hat plus sine theta in the y hat. And that is k positive q over r squared times this. So since an electric field tells us the direction that a positive charge would move, we want this to point to the right and down. So we define up and to the right to be our positives, then we would actually want this to be negative sine of y, or sine of theta times y hat. So yeah, let's write this as our vector for E from plus Q. Now, we should be able to do the rest of them a little quicker. So E from minus Q will be K times negative Q over R squared. This is going to point to the right in the x direction, so positive cosine theta x hat, and oh, wait a second, no, it's negative. This will take care of that. And then up in the y direction, so positive sine theta y hat. Let's think about that for a second. If we let this point up, the negative will make it point down, which matches what this positive charge would do. Okay, yeah, that works out. Now let's look at the field from positive 2q. It's going to be k times 2q over r squared. This will be pointing to the left in the x direction, so negative, and it'll be pointing up in the vertical direction, so positive. And finally, from minus 2q, we'll point to the left in the x direction and down in the y direction. Okay. So finally, now we can actually think about adding all these together. So we'll want to add all the x hats and all of the y hats. So in the x hat direction, every term is going to have a cosine theta. Since they're all going to be broken up based on 45-degree angles, those cosine theta should all be exactly the same. So really what we're adding and subtracting is the multiples of q. So from here we have a plus q, here we have a minus q, here we have a minus 2q, and here we have a plus 2q. So that's actually going to cancel out all of them. So in the x hat, we're going to end up with a net electric field of 0. Then in the y hat, we're going to have a negative q, a negative q, a plus 2q, and a plus 2q. So that gives us negative 2 plus 2 plus 2. So overall it will be negative 2q in the y direction. So that tells us, okay, we have a little more room down at the bottom before I erase everything else, that the net electric field at the center is going to be K times 2Q over R squared times sine of 45 in the y-hat direction. Right, we had -2, +2, +2, yeah. And there is no x component. It has 0 in the x-hat direction. Now, let's go ahead and get a number for it instead of doing that at every step of the way like I was about to do earlier. This electric field will be 9 times 10 to the 9 times 2 times 10 to the -8th over 3.5 times 10 to the -2 meters, but squared, times the sine of 45, also known as the square root of 2 over 2, in the y-hat direction. Okay. Hello, Bestowal Pants. Thank you for your question about EMFs. So, 2 EMFs in opposite directions. What that would do, I believe, is basically like undo a change in voltage. So, I'm just gonna a little box here. So if we have a circuit with an EMF here that takes us from 0 volts to like 3 volts, so this EMF is plus 3 volts going from negative to positive, and then we had another one over here I'm actually not sure how this would work on a single loop circuit. Well, if we had another one, so this is 1 and this is 2, we know that the sum of the change in voltage has to be 0. So we could say that EMF1 plus EMF2 has to be 0. So then if EMF1 is plus 3, then that means EMF2 has to be -3. So that's the first sort of quick example I could think up, but I'm guessing you probably have some problems with more complicated circuits than this, as is usual. But yeah, I think all that should do is just, you know, they're effectively fighting against each other. So if one is raising the voltage up, the other one is going to have to bring it down in the opposite direction, assuming they're in series like this. I'm going to work on punching this into the calculator still. If you have more questions about the EMFs, or if you have a specific circuit you want to look at, then feel free to let me know. Does it lower the total current? That depends. Like, let's see. If we do this, we can say for the entire circuit that delta V equals I R equivalent. Actually, I should have two resistors for that, R1, R2. Let's see. So this equation is going to describe the current for the entire circuit based on the resistance from both of these. Question is, where is this delta V defined? I think it would be based on yeah, it's really hard to say if having EMFs in the opposite direction would lower the total current just in general. I'm having a hard time trying to come up with an example circuit that actually makes sense to sort of work it out. But I think probably the idea, or maybe what whatever homework question you're working on is getting at, is that if you have EMFs working against each other, you're not gonna have the same magnitude of voltage. And so if the left-hand side of this equation is smaller, the magnitude of the voltage, then this would also have to be smaller. So I think probably what that question wants you to get at is that yes, it would have lower current, but it's hard to say for sure in general without looking at specific circuits. So that gives us overall a 10 to the first power on top and 10 to the fourth on top, so this is 10 to the fifth again. Volts, actually we're going to put the y hat first, then volts per meter. There's our final answer for the electric field problem. No problem. If you have any other questions you'd like us to work on, still got about 10 minutes left in the stream, so we could work on that before I start another random problem. thank you for being a return viewer and asking the second ever homework question in the history of this live stream. Okay. Let's maybe do a quick little integral. Okay, this one could be interesting. Oh, that's weird. This is d dx of x cubed. No, wait, I'm looking at the wrong one. X to the fourth times the cube root of x squared plus 9 dx. Oh, a math question? Go for it. Suppose this is a good time to actually take off the notice that I'm just working on random problems. Give us a little more real estate on the screen. Okay, yeah. So, trig integrals, I'm assuming you are talking about ones where we get like sine to the 5th of x, cosine to the 7th of x, dx. And there is a pattern to these that we can try to do in general. So it's all going to be based on when we say if we let u equal sine or we let u equal cosine. So what is going to end up here is du will equal cosine x dx, and here du will equal the sine of x dx. So what we want to do up here with whatever, you know, powers of sine and cosine we have is we want to break one off to the side. So maybe we'll break off cosine to the first power over here. So like in this case, we would say, okay, let u equal, okay, wait, there's more simplification we have to do before we do the substitution. So we want to turn everything else over here in terms of sine. So when we say u equals sine, all that's going to be left here is a bunch of u's. And so we're going to have to do that with the sine squared plus cosine squared equals 1. We need to get this to be some form of like cosine squared, because then we can say cosine squared equals 1 minus sine squared. So cosine to the 6th, we could say that's really like cosine squared but to the 3rd power, because then when we have a power, you know, something in parentheses raised to another power, those powers just multiply. So this will be sine to the 5th x cosine squared. Everything inside of this parentheses is actually 1 minus sine squared. Still to the 3rd power. And then we have cosine of x dx. So now we say u equals sine. So du is cosine dx. So right there, du just eats up this part, and everywhere that we have a sine earlier in the integral, that becomes a u. So we have u to the 5th, 1 minus u squared, and then cubed du. Now it's going to be a pain, but it's just a power rule integral that we can do with our basic power rule. So the pattern is, you want to see which of your trig terms you can basically do this little exponent trick with and turn it into the other one using this identity, and then whichever one you have made your main one over here, you let u equal that one and peel off an extra of the other trig function to be absorbed into your du. And you can do this same kind of pattern with like tangents and secants, and I think some other ones too, but you'll probably see sine and cosine the most times. Yeah, I think we could also do it in terms of cosine. Let's think about that. So if we want to have our substitution be u equals cosine, then we need to have a sine sitting over here at the side. So that would need to be sine to the 4th. We would have sine of x here. This would be cosine to the 7th still. And then we would play our exponent game here. We would say that sine to the 4th is really sine squared, but squared again. And then we can say up here that sine squared x is equal to 1 minus cosine squared x. So inside of that parentheses, we have 1 minus cosine squared, and then we have cosine to the 7th, and this is a sine now. So if we let u equal cosine, du would be negative sine, and all that would change is we would just get an extra negative sign in front of the integral, and actually we'd have a slightly different polynomial. It would be 1 minus u squared times u to the 7th. But it's still the exact same process, or the same sort of strategy, the same game, to break it down into this polynomial form at the end. So yeah, a lot of times with those, you can do them in terms of one or the other. That won't be doable in every example. Like if this was signed to the fourth, then when we take this extra sign away, this would be, we would only have sign cubed left. And because that's an odd power, we can't do this same game that we do using our identity. So if you had sign to the fourth, then you would basically have to do it by breaking up the cosines, because then you can write, you can write this in terms of that again. So if you have an odd and an even power, then you want to pull away the odd term, pull an extra off of the odd term. If you have both odd powers, you can pull away either one of them. And if you have both even powers, that's when it gets a little hairy, and you usually have to end up using like some double angle formulas or some reduction formulas, which hopefully your textbook or your professor has told you about. So it's actually time for me to end off the stream here, but thank you for tuning in again and asking good questions. I hope this example integral was helpful, even though we didn't solve it all the way to the end. I hope the process of the trig solving was clear enough. So we'll be back on Thursday at the same time. So until then, have a radical day.